Hello, today we will continue our lecture series on the basics of nuclear chemistry, and today we will talk about the very important topic about radiation safety and dosimetry. And it is important because we know that the consequences of ionizing radiation can be quite harmful, and it can be like long-term effects like cataract or cancer, or it can be immediate effects like skin damage or other effects. Where does this ionizing radiation come from? Of course, first of all, it is professional work with radiation sources. It can be staff on nuclear facilities, or it can be medical personnel who are working with sources of ionizing radiation. And of course, we are all living in the sea of radiation, so the radiation is everywhere around us. And can natural radionuclides be harmful? And the answer is yes, because if they are concentrated and they are handled unsafely, that means that the flux or doses of ionizing radiation can be too high, and these doses can be harmful. If we will look back in the history, just after the radioactivity was discovered, it was like a miracle for everyone, and a lot of different applications were for to apply these novel materials, novel unknown rays, and it was thought that this new unknown rays can be useful, can be used for the health or as a source of energy for a human being, for example. And there are examples of water with radium, chocolate with radium, or some bath salts or toothpaste or whatever with the content of the natural radionuclides, but concentrated natural radionuclides. And it was not always fair advertisement. For example, this toothpaste, Toradia, was advertised with the name of the Dr. Alfred Curie, and this man, this doctor, it was his real name, Curie, family name, Curie, but he was not related directly or indirectly to Marie and Pierre Curie. And Marie and Pierre, of course, were already well-known scientists, and this name of Alfred Curie was used as advertisement, but this man was just, let's say, nobody, just a common doctor. The most known example of unsafe treatment of natural radionuclides in the early years of 20th century is so-called case of radium girls. It was a company who used the special colors, special paints for to produce different equipment for airplanes and for Navy and for other military purposes, and not only, but the main idea was to use these paints to put them on the arrows or on the scale of this equipment, and these paints they eliminate visible light under the action of radioactive decay of radium. So it was and these paints they were covered. They cover this equipment just by the brushes, and these girls they used the mouth to make brushes very thin, and that they can put the very thin lines on the numbers, for example. And of course, all the radium or big part of big amount of radium were introduced in the bodies of these girls, and it caused some diseases, some cancer, and around 4,000 people were exposed to this radiation and were harmed. And it was the first known case of mass exposure to radiation and mass harms for due to the radiation. And another example is use of the X-rays just in common stores for shoes. They used it to make it easier to see how the shoes fitted to the foot, and so it was like this procedure. The customers put the foots in shoes and then make a photo or image, X-ray image of the shoes, and it was easy to adjust the shoes to choose the specific shoes for specific fits, let's say. But as far as many of the employees of the staff of these shops, they got this disease, cancer diseases. All these equipments were cancelled, of course, were banned, because when the clients came to the shops, they make this procedure maybe once or twice, so the overall dose from these X-ray tubes was not so high, but the people who worked at these shops, they make this procedure very often, so they got quite a huge dose of ionizing radiation, and it had very negative effects on their health. Another cases, it's already a specialist who worked initially with this equipment. First is assistant for Edison experiments. He produced these X-ray tubes for experiments and tested them, and he died quite in young age due to the aplastic anemia. And another famous example is Marie Skłodowska-Curie, who worked with large amounts of radioactive materials, but that is also important that she used to work as an X-ray assistant, a medical assistant during the war, and so she worked in the front line, and due to these procedures, X-ray procedures, she also got some quite high doses of irradiation, and she died also of aplastic anemia. And another case that is not related either to scientists or people who used in the work the radioactive samples. It is the case of quite a rich man with a good health, sportsman, and as far as he was rich, he was able to buy a lot of the medical preparate, medical solution called Raditor. It is actually radium salts dissolved in water, and activity of one bottle is about 1 microcurie, but he was able to buy a lot of such bottles, so it was more than 1,000 bottles. That means that the activity of the consumed radium was around 1 millicurie, and it was enough for him to get the cancer and died due to the anemia as well. So why all these cases were in the past? First of all, of course, it's a lack of objective knowledge, because the ionizing radiation was quite a new phenomenon, and there was no data on how it affects the human beings. Or it was non-compliance with the safety standards. So that means that even if people knew how to use the radioactive samples properly, safely, they work without with non-compliance of this with these safety standards. Or it was just a misuse of these radioactive materials, like in the case of this rich man. Before we will go to the effects, how the different ionizing radiation affects the body, the organisms, I will remind you that different types of ionizing radiation interacts with the matter in different ways. And for us, it is important that alpha and beta particles, they have quite a small, short range in the matter, and thus, if the source of ionizing radiation, if it is alpha or beta emitters, and they are outside of our body, that means they are practically harmless if it is pure alpha and beta emitters. But if we inhale or if we eat alpha and beta emitters, that means that they entered into our body, then they will produce the main dose, because all the energy will be absorbed by the human body. And what is the influence of ionizing radiation on living organisms? First of all, it is production of active molecules, radicals, ions, or it is changes, and then it is changes in biomolecules. To understand how many active radicals or ions or other processes are undergoing as an effect of ionizing radiation, there is a special quantitative characteristics called radiochemical yield. So again, it is the quantity of created molecules or created ions or destroyed molecules, or any other changes in different parameters that we can measure. It can be angle of rotation of the polarization plane, or it can be conductivity of our material or whatever. And all these changes that are caused by the certain amount of energy, so it is the radiochemical yield. And it is measured either in mole per joule of the adsorbed energy, so mole of molecules destroyed or ions created divided by joule of energy that is absorbed, or it is a standard unit. It is molecules per 100 electron volts. And there is a simple relationship between these two units. So one molecule is around 0.1 micromoles per joule, or vice versa, one micromole per joule is equal around to 10 molecules per 100 electron volts. The values of radiochemical yield can be different. It can vary from 0 or from some parts of molecules per 100 electron volts to dozens of molecules per 100 electron volts. As a result, all the living organisms, they contain a large amount of water. And as far as there are a lot of water molecules, the main first action of ionizing radiation will be radiolysis of water, formation of radicals and other active particles and that can interact with biomolecules, and thus changing them, oxidizing, or it can be substitution of different functional groups or cross-linking between the biomolecules. And the result of all these changes is the abnormal work of these biomolecules. That means that abnormal work of tissues, organs, and finally the whole organism. And the weakest part of our cells is the DNA. It can be a direct effect of ionizing radiation. Then it goes directly to DNA molecule and it can break one or two chains, or it can be indirect effect. Indirect effect, it is the formation of radicals in water from water molecules, and then the action of this active species onto DNA molecules. Thus, later these consequences can be very different. We know that the DNA molecule itself, it is a two-chain molecule, but it's not only the molecule. There are also some molecules, protein molecules around the DNA, and they are working together, let's say. And the result of these effects of different direct or indirect effects can be this cross-linking between the DNA and the protein molecule, or it can be cross-linking between the protein molecules. Anyway, the DNA didn't come to initial state, and thus it can be mutation or death of the cell. And it is interesting, it is so-called radiobiological paradox, that the energy that is enough to kill the cell is so small that it would lead to the heating of the cell only to 1/1000th of the Celsius degree. So you can see that the energy is very small. The energy that is enough to kill the cells is very small if we compare it to the just a thermal energy. And all the radiation protection systems, they have three pillars. First of all, justification, Alara principle, and the dose limits. What is justification? That means that if we can make some procedures without use of the ionizing radiation, then we should do it without ionizing radiation. Or if we cannot exclude the use of ionizing radiation, then the positive effect should be more or bigger than the probable possible negative effects of action of ionizing radiation. One of the example is the use of ionizing radiation in medical procedures. So if the medical diagnostics can help to treat the illness of the patients, and the possible negative risks will be negligible related to the positive effect, then we should use ionizing radiation like X-ray or whatever. The LRA principle, or that means that we should, if we will use ionizing radiation, so we already passed the justification process, we will use ionizing radiation, then we have to use as low doses of ionizing radiation as reasonably achievable. What means reasonably achievable? It means that we should take into account economic effects, social effects when we use ionizing radiation. For example, if we will use very low doses of ionizing radiation, but the treatment or diagnosis will take months or years, that means that it is not reasonable to use such a low doses. So we should increase them to the limits when it will be reasonable to use them. So they will be still low, but as low as we will reach the positive effects when we will use them. And those limits, of course, we should control how much of ionizing radiation we will get. So there are several relationship between different dosimetric quantities, and we will go through all of them. So first of all, it is measured quantities. It is in fact just an instrumental response, so that the signal that comes from the detector. It can be current, electric current, or it can be some other parameters that we can light emitted or whatever. From these measured quantities, we are going to operational quantities, and from them we go to the protection quantities. That so it is quantities that are used to say if our operation is safe or not. And all these doses, either operational or protection, they of course are related to fundamental physical quantities, and we will start with these fundamental quantities. So the main parameter is the absorbed dose. In principle, it's just the energy of ionizing radiation that is absorbed in the matter, and this energy we divide just by the mass of this matter. The absorbed dose we use for any kind of ionizing radiation, alpha, beta, gamma, neutrons, whatever. And for all the kinds of the matter. It can be solid, gaseous, it can be liquid, and etc. And so we use the unit to measure this absorbed dose, that is joule per kilo, or in standard units it is called Gray, so named after the physicist Gray. There is another quantity called kerma, or it is just abbreviation of kinetic energy released per unit mass, so kerma. And in principle, it's just the quantity that is used to measure the energy of the charged particles that were produced as a result of action of non-directly ionizing radiation, indirectly ionizing radiation. So it is used to measure the effect of gamma radiation or X-rays, and the unit of this quantity is also Gray. So what is the difference between the absorbed dose and kerma? Again, that absorbed dose is used for any kind of ionizing radiation. It can be directly ionizing radiation like alpha particles or beta particles. That means that the ionizing radiation that brings the charge to the matter. And kerma is used only for indirectly ionizing radiation. So it's ionizing radiation without charge. So X-rays, gamma, quanta, and neutrons. And again, kerma is the kinetic energy of the charged particles that are resulted from the action of indirectly ionizing radiation. In principle, for our purposes, when we are speaking about the gamma rays or X-rays that are coming from the radioactive sources like radionuclides, the energy of photons, gamma, quanta, is small and so less than 3 mega electron volts, and in this case we can assume that kerma and the absorbed dose are equal, because when we talk about the kerma, part of the energy of these charged particles that are produced can be converted to the, again, indirectly ionizing radiation. I'm talking about the Bremsstrahlung radiation or stopping radiation. So just imagine that your X-ray or gamma quanta comes to the matter. So it's indirectly ionizing radiation come to the matter. It produces the electrons or other charged particles, and then electrons stopping and producing Bremsstrahlung radiation, that means electromagnetic radiation, or indirectly ionizing radiation. So part of the energy that will initially transferred to the charged particles will be converted back to the indirectly ionizing radiation, and thus the kerma, so we will let's say, lose a part of the energy due to the production of, again, indirectly ionizing radiation. But it makes sense only for high energy of photons, more than, let's say, 5 mega electron volts. But in our case, as I said, we can say that kerma and absorbed dose are equal. It is not the case when we used special accelerators, but in general we can neglect it. Radiation exposure, this quantity is not longer in use. So in principle it's just a total charge generated in a dry air by X-rays. So again we decrease our types of ionizing radiation and the matter. Now it is only air and only the total charge that is produced, and thus we cannot directly use it to measure the absorbed dose in the organism, because air and the tissue, biological tissues, they are a bit different. And the unit is a coulomb per kilo, or it is non-standard unit is a Röntgen. I'm quite sure you heard about this value. So now we will go to protection quantities. So what we use when we talk about the protection of our personnel, of the population. So first of all, it is absorbed dose in an organ or tissue, and it can be used when we speaking about the non-even distribution of the radiation through the body. If we irradiate only hand or eyes or lungs, we can use this absorbed dose in an organ or tissue. Another quantity is equivalent dose. That is quite important quantity because in this case we are assuming the different actions, the different effects of different types of ionizing radiation. So we know that alpha particles, they're heavy particles and they have the highest ionization ability, and thus they can harm tissues, biological tissues, more efficiently than beta or gamma decays, and thus there is a special weighing factor that takes into account these different effects of different types of radiation. To calculate the equivalent dose, we simply multiply this weighing factor and absorbed dose. And you can see that for photons and electrons, the weighing factor is the same, is equal to 1. So for gamma quanta and for beta particles, we can say that the absorbed dose and the equivalent dose, they are equal. But alpha particles, as I said, have the highest weighing factor. That means that they 20 times more dangerous, more hazardous than gamma quanta or electrons or beta particles. And for neutrons, depending on their energy, this weighing factor can vary from 2 to 20. And just to note that this letter R is related to the radiation type. So when we will see later, there will be different weighing factors, and these indexes, they will show you about which dose we are talking now. For example, the next protection quantity is effective dose. Again, if our body is irradiated unevenly, that means that we irradiate, for example, only one organ or some part of our body. That means that we should use the specific sensitivity of the organ that was irradiated, and we recalculate this effective dose knowing the equivalent dose with the weighing factor. And you see this letter T is related to the tissue. Thus, these weighing factors, they show us how different organs and tissues are sensitive to the ionizing radiation. And you can see from these examples that the organs where the cells are always produced or they have the highest sensitivity. So, for example, skin, the skin cells, they are not so often renewed. That's why, and there are some specific mechanism in skin cells to withstand the radiation, because we always irradiate our skin with the sunlight, and thus the sensitivity, the skin cells is the lowest. Again, the organs where the cells are constantly renewing, they have the highest sensitivity. So it is more dangerous for them to be irradiated than for other cells. And you see that we multiply this weighing factor for tissues, and if the whole body is irradiated evenly, then the sum of all this weighing factor is equal to 1, and when we are talking just about the equivalent dose. Okay. Now, operational quantities. They're used as a model of a human body when we, let's say, so ambient dose equivalent, what it is. We have this spherical phantom that is produced, so it is a physical object that is produced from a special material that has a composition similar to the biological tissue with the close average effective charge and density, and the composition of this material is very close to the biological tissue. And we irradiate this phantom, this material, with the same source of ionizing radiation, with the same flux and the same distances. And we will see what is the dose that will be produced inside this phantom at specific depth. And this specific depth, this D notation, they're different if we assume the whole body, when we take this depth as 10 millimeters, for example. Or if we are talking about the eyes, then we, of course, the eyes is a very small object, and we related to the whole body, and we use 3 millimeters depth to calculate the equivalent dose inside the eyes. Or if it is hands, we use 7 millimeters, for example. And we can calculate, even without measuring the dose rate from a point source of gamma radiation, if we know the composition of this source of ionizing radiation. Because if we know the composition, the energy of the gamma quanta that are emitted, then we can calculate this constant that is called Kerma constant, for example, and so just or gamma constant. This constant is specific, so we can calculate it for the certain specific radionuclides. If we know the energy of the gamma quanta, we know the yield or intensity of this gamma quanta due to the decay, and we know the absorption coefficient for the gamma quanta with this energy. You can see that if we know all these parameters, first of all, we can calculate this constant value, and also we can use a database where all these constants are already calculated. But if we just know the energy of gamma quanta emitted or X-rays, for example, if we have not a radionuclide source but accelerator source of gamma quanta or X-rays, when we can use this equation to calculate this constant, and then using this constant we can calculate the dose rate if we know activity or numbers of disintegration per time, and we know the distance from our source. And this constant, the units is Atto Gray multiplied by squared method and divided by second and becquerel. And Atto means the 10 to minus 18. So we know nano 10 to minus 9, we know probably femto 10 to minus 15, and there is Atto Gray, so 10 to minus 18 grays. When we would like to recalculate the dose rate that is calculated for an air conditions, and we would like to calculate what is the dose rate or dose in tissue, then we have to calculate this ratio of absorption of gamma quanta with this energy in tissue and in air. And actually this ratio deviates not very strongly. It deviates only from 6 to 12% for photons of different energies. So you see this broad range of energy from 4 to 15 mega electron volts. And these deviations is only from 6 to 12%. But as an average value we usually take the value 109, so as average between these two in this region. When we irradiate the material or body with the external source of gamma radiation or X-ray radiation, we are talking about the kerma values. Remember that it is energy of the charged particles that are produced by the indirectly ionizing radiation. But these charged particles then produce all the effects further inside the body, and thus the dose is related to the is dependent on depth of the penetration of the photons, not as an exponential decay like kerma. You see that kerma is decreased as exponential with exponential law, but the dose is formed in the very small in the very beginning. The dose rate is just accumulated, and at certain point the dose rate and kerma becoming let's say equal to each other, and from this depth dose rate is decreasing with the exponential law as well. And I remind you that it affects on the use of the photons for treatment of cancer, for example. This is an example of how dose is changing when it produces by photons, and if it is produced by protons or alpha particles. For heavy charged particles, there is a Bragg peak. We remember about this Bragg curve, when all the energy, almost all the energy, is absorbed in the very narrow part of the range of protons or alpha particles. And that is also important that in the case of gamma quanta, we are not talking about the maximum range, because it's exponential law of absorption, and it lasts for almost for forever. But for protons and alpha particles, there is a specific maximum range, and all the particles, they are stopped at this range, and no particles are going further. And it affects on the distribution of the doses that are produced by photons. You see that even the health tissues, they're exposed to irradiation, because doses, they are not stopped doses that are produced by X-ray and gamma, so they are going through all the tissues. But protons or alpha particles will be simply stopped at a certain point at maximum range, and thus all the health tissues will not be affected by the ionizing radiation, and thus the doses for healthy tissues will be lower. What is the effect that is produced by a certain dose? There are two classes of effects: the deterministic effects and stochastic effects. Deterministic effects means that after a certain dose, it is high doses, more than 0.1 gray, we can say what the effect will be from a certain dose, and it is a negative effect and certain determined effect, either skin damages or eyes damages or other damages of the health, stopping at the death of organism. So at higher doses there are no more effects because the body is already dead. And stochastic effects, these effects are probabilistic effects. That means that due to the some doses, the risk of some negative effects, like cancer, for example, is increasing. So it's only risks. It's not a certain person who will got the cancer, because when we talk about the stochastic effects, that means that we are speaking about a huge group of people. It's not 10 or 20 people, it's thousands and millions of people, and we can speak only about the probability of the overall cancer cases in this huge group after average dose will be this, for example. So that means that if we have an increase in cancer risk of 1%, let's say, that means that among 1,000 people, 10 of the people, we don't know who exactly, but 10 of the people probably will get the cancer cases related to the ionizing radiation in 20 or 30 years, for example. And the deterministic effect, they can be local or common effects, as well as late effects, and as well as stochastic effects. Stochastic effects, again, it is the region of low doses, let's say less than 100 millisievert, and there are several models that can be used to determine the probability of negative effects depending on the absorbed or equivalent dose. But the recommended by the International Committee on Radiation Safety recommended model is a linear non-threshold model. It is this black line going to the zero. That means that any addition of the dose will cause the increase in the risks of negative effects. And we know from data, from experimental data, let's say, this linear relationship that is going to low doses, but at very low doses, less than 50 millisievert, let's say, we don't know exactly what is happening, because in this region it is very difficult to separate effects from the natural radiation and to the additional doses of ionizing radiation. And for example, where we can get this data, first of all, this data for this linear relationship came from the database of the health state of the people who survived the nuclear bombardment in Hiroshima and Nagasaki. During the long period of time, it was investigation of their health, and every person, it was estimated the dose that every person got, and so it was known the dose and the effect on the health. for these persons. It is a first database. The second is, of course, the workers, the personnel of the nuclear facilities. It can be nuclear power plants, it can be nuclear fuel reprocessing or nuclear fuel fabrication plants. So all the workers who are dealing with radioactive substances, they have personal or individual radiation control. So we know the doses for every person. And also every year they have a medical examination, so we know the status of the health. And this is a huge database in Russia, in Europe, and USA. And another class of the databases is patients who are treated with ionizing radiation, either it is X-ray or gamma ray knife, or it can be some radiopharmaceutical diagnosis and treatments as well. So you can see that it is a very huge database, and we know this linear relationship to a certain doses. But in very low doses, there is some debates on how the ionizing radiation affects on the human beings. So first of all, it's just a linear non-threshold model. Another is a supra-linear model that says that at these low doses, this addition of doses has more negative effect than just a linear model, because in this region, it is just a theory. In this region, organism cannot recognize this small addition of external doses, and thus the organism doesn't react on these additional doses. But additional doses create some negative effects like formation of radicals and certain etc. etc. But organism doesn't feel these negative effects, and thus in total these negative effects accumulates and produce more hazard to the human health than we assume in linear model. Another theory that small doses, you see this, have positive effect on the human health. Why? Because we heard that small quantities of poisons can be used as medicine, and so the small quantities of some stressors they can serve as a like catalyst for immune system, and so they always keep our immune system in tonus, and thus the small doses may have a positive effect. But all these hypotheses, they are still hypotheses. We cannot. It is very difficult to treat this data statistically because we cannot exclude the natural background radiation, and we cannot calculate statistically reliably the addition of small events, small amount of cases in the case of very low doses. So for deterministic effect, there is some certain effect depending on the received dose, on absorbed dose. When it is 100 millisievert, then it is doubling rate of gene mutation. At 1 gray, we can say about the radiation sickness already. At 3 to 5 grays, it is like LD50 for chemicals. That means that 50% of the human beings who are exposed to radiation will die in 1 to 2 months, and at doses higher higher than 10 gray, we can say that it is lethal dose, and death will occur certainly, but the time of this death will vary according to the absorbed dose. How we can control our dose rates? Of course, we used for this different types of dosimeters. Very often, so it is used almost in every facilities. It is so-called thermoluminescence dosimeters. The principle is that these materials, the list of them is here, and one of the most popular is this lithium fluoride, because its average charge is very close to the biological tissue, so around 7. And these materials, they absorb the energy, ionizing radiation, energy of ionizing radiation, and when this material, after absorption of ionizing radiation, then these materials are heated, they emit just a visible light that can be detected by photomultiplier tubes or whatever. And with the intensity of this emitted light, we can recalculate this intensity to the absorbed dose. Another system that I used in medical procedures, it is ionization chambers. So it is like chamber, ionization chamber. When we talk about the detectors, the charges are produced inside the detector, and we can recalculate the number of charges to the energy that were consumed to produce this amount of charges. Another promising technology is called optically stimulated luminescence dosimetry. So in this case, absorption energy is released in the form of visible light, but in this case we use not the heating of the material, but the irradiation with the laser. So it is much quicker, much easier, but there is some problems, because the material, the corundum aluminum oxide, its density and average charge is far from the biological tissue. So we have to recalculate the absorbed dose from the intensity that we obtained, recalculate from this material to biological tissue. There are some other plenty kinds of dosimeters that are used in different fields. For example, chemical dosimeters like Ссылка or radiochemical films, they are used to measure quite high doses from 1 to several thousand grays. Another type of chemical dosimeters is some polymers. Again, it is you can see the phantom that is produced from the special material that you see this cloudy formation under the action of ionizing radiation. So we can analyze the absorption dose and the distribution of the dose through the body. So it is used to simulate the distribution of doses through the body under the certain irradiation by X-rays or gamma rays or other medical treatments. Some other diode dosimeters or field effect transistors, they are used in the cases when we should use very small dosimeters, because we can make very small diode dosimeters with the size of few millimeters. And some others, like radiographic films that are used in X-rays, study treatments, diagnosis, and many others dosimeters that are still developing to generate the smallest and the most efficient dosimeters. How we can protect ourselves from the ionizing radiation? So again, there are three pillars: time, distance, and shielding. With this picture, I would like to represent and remind you that the ionizing radiation is going from the source of radiation, not like just a narrow stream or a plane. It goes in all directions like a sphere, and thus the energy of the ionizing radiation is distributed by the surface of this sphere, and thus the surface of the sphere is 4πr squared. And thus, if we increase the distance from the source, that means that we increase the radius of the sphere, we decrease the dose rate. And it is a squared distance from our source. That means if we increase the distance 3 times, then the dose rate will decrease 9 times. If we increase the distance 4 times, we decrease the dose 16 times. And we remember that the dose rate can be calculated using this simple equation. Again, this is distance squared, but also the time. You see this time. That means that if we cannot increase the distance because we have to work with our hands, for example, we can reduce the time that we spend with this source of ionizing radiation. Or if it is possible, we can decrease the activity of our source. If none of these are possible, no time decrease or the distance increase, when we have to use shielding. And it can be done in different ways. If it is gamma ray source or X-ray source, we can use just a LED bricks or sheets or whatever, or we can use a special glasses. This just a representation that one glasses with LED can be as efficient as this few layers of conventional glass. And of course, these huge hot cells, hot cameras, hot cells, where operators are working with manipulators and these very thick glass, LED glasses that are weighing like 1 or 3 tons. That is quite impressive shielding. But we have to remember that not in all cases we have to use the LED. For example, if it is again pure alpha emitters that have small range, we can use just gloves and respirator to prevent inhalation. If it is pure beta emitters, when we have to use light materials like plastic glasses or aluminium, but not the LED, because we have to remember about the Bremsstrahlung, and that means if we have a very dense material that efficiently stop electrons or beta particles, that means that we will produce quite intensive stopping radiation. For gamma radiation, of course, in this case, we have to use LED or some other dense material like concrete. In some cases, we can use even the depleted uranium, because it is more dense and has a higher effective charge than the lead, and thus uranium will absorb gamma quanta more efficiently than lead. But of course we can use it in some specific cases when the irradiation, gamma irradiation, is very high. And for neutrons, we can use the materials that have a lot of light atoms, like hydrogen. Of course, it's water, first of all, then plastics or wood or other material with with high concentration of light materials. Here, in this picture, is the representation of how different shielding is working for different types of radiation. So this is all for today. Thank you for your attention and see you next time.